we're going to look at the properties of logarithms. This is where students are not as strong. The exponent rules are a little better on, but here is where it falls by the wayside. Properties of logarithms. Well, they actually come from our rules of exponents. So if I just put them over here, there are analogous rules for logarithms as there are for exponents. Remember, we had, a to the n times a to the m, a to the n plus m, a to the n raised to the nth power, a to the n times m. We just used that a couple of times. 3, we have a to the n over a to the m, a to the n minus m, etc. There are analogous rules for the logarithms, or properties or rules of logarithms that we will derive and show. Let's just derive this first one that's analogous to that. So let's use, instead of n and n, let's start with property 1 over here for exponents. 1 for exponents. And instead of n and m, I'm going to use a and b, because that's what we want to use in the end. So let's take the rule, which says little a raised to the a power times little a raised to the b power. Doing this same exact rule over here just gives me little a, my base a, raised to the a plus b. So I start with my property 1 from my rules of exponents. And now let's let the following. Let's let my a here equal to the log in the base a of x. We're going to use this for a second. Okay. So we'll do that with the corresponding exponential definition. So this has an exponent definition. This also means, a to the a, if you will, is equal to x, or x is equal to little a to the a. Remember, we can either write it in logarithms, or we can flip it this way. A to this power is the exponent. This is my exponent definition of a logarithm, because logarithms are really the exponents. So in a similar fashion, we also have, similarly, we have b is the log in the base a, and I'll call that y, if you will. Or giving my other definition, I get y is equal to a to the b. Okay, so what do I have? Let's plug everything in and see what we have. If we wanted to, let's define a c now. So these are defined, and let's call c, and that's going to be log in the base a of x times y. So we're just kind of creating, logarithms, and then we're going to see how this can be transformed into a rule for logarithms instead of a rule for exponents. This is equivalent to the other, definition that x times y is equal to a to the c. Okay, so let's start with that. So this is nothing more. So this is our beginning stuff. This is all our definitions of what we're going to look at. So let's start with this. This is we know this is true, but a to the a is just x. So this is x times, well, there's a to the b, that's just y. Okay. It's equal to my a to the a plus b. Well, let's see, how do we kind of transform that? We have that this is nothing more than, we'll call this is nothing more than x times y. So this is x times y. So this is x times y, right? Which we know x times y is a to the c power. So that's given from over here. X times y, which is a to the a times a to the b, is equal to x a to the c. But according to this is nothing more than a to the a plus b. I'm just using this property of our exponents, but with these logarithms defined appropriately. So this tells me here, same base, that means c has to equal a plus b. Both of those exponents have to be the same. Same base, same exponents. But what is c? Well, c is my log in the base a of x times y. What is a? Well, a is my log in the base a of x. What is b? So I have plus now. Plus b is log in the base a of y. This is my first rule for logarithm. The logarithm of a product is the sum of the logarithms. So that's what we get. We can get rules and that come from the exponents because we know logarithms and exponents are related. Now, I'm not going to have you derive these rules. We're going to learn how to use the rules. Here's a proof of these rules. So I just proved that the log of a product is the sum of the logarithms of the individual terms over here. So that's what you have. There's our first proven property. And these are properties that are directly related to the properties of exponentials. Now I gave a short proof of the first one yesterday. I won't give you the proofs. They're in the textbook. For these other ones, we're going to learn how to use them. But they stem directly from all the properties of the exponentials. So what we have is we have properties of exponentials that we went into prior in 9.1. And those are as follows. I'll put them in the order I put them in the book. Sometimes you see them in different orders. And we use x instead of n and m. You can add the exponents. Or if you're dividing, as long as it's the same base, you subtract the exponents. Then if you raise to a power, you multiply. And in addition, let's see, you have the following, that if I raise anything to the 0th power, that is just equal to 1. Those are the predominant ones that we use for the exponential properties. And what we saw on Tuesday, I derived a special property that's related to this as a correlation for the properties of the logarithms. The one that correlates with this is that the log of a product is the sum of the logs. So if I take the log in the base a of the product x times y, it's equal to the log in the base a of x plus the log in the base a of y. Because in essence, what you see, it turns a multiplication into a summation. And we have a correlation over here. This is a sum, and then we have a difference formulation. So we have the log of base a of x over y. Using the same method of proof that I did on Tuesday, you can show that this is equivalent to the following. X minus the log in the base a of y. And that's a direct correlation for that rule of exponents. We have another one over here, which is I have the log in the base a of x to the r. Well, I can bring that exponent, it's not outside of the logarithm, it's in the argument. But that r is in the argument of the logarithm, and it comes out as this, the log in the base a of x. And we can also show the following, which is if I take the log in the base a of 1, this is a correlation to this rule over here, that's equal to 0. Now we have two additional logarithms, and they don't they have a correlation for exponential, but we don't really use them for the exponential. And one is this. I'll put it in here. Let's go use the other red now. And this is running out of juice there. So here's rule number 5 that we could use if we wanted to. And you can say the log in the base A of A is equal to 1. Now, what would that correspond to over here? If I wanted to write a rule, that would just be, A to the first power is equal to A. But we don't have a special rule. You could write it there, but it's not necessary. But those are the rules that we will use frequently. And there's one additional rule that we have, and it's called, I'm going to, use these rules to prove that rule, and that rule is called the change of base rule, if you will. So let's take a look at the last rule over here. Really is, we'll call it rule 5, 6 or something. It's the change of base rule. Now, this really was necessary, especially with calculators that didn't have all the various bases in them for the logarithms. They only had a base 10 and the natural base, the natural log. And the idea is this. Let's kind of show what we mean. Let's let the log in the base b of x equal to y. Okay. Now, this also has an exponential form. So if I wanted to rewrite this in exponent form, remember we have, that's the name, the logarithms are really exponents, and that exponent form is my b to the y is equal to x. I can either write it like this or like this. These have the same meaning. Given a base b and a value x, I want to find the exponent y because logarithms are exponents. So this and that mean the same thing. So let's start with this now. I've transformed that into this expression over here. And what can I do? Well, I can take the logarithm of both sides of that. So let's do that. So I'll take but now I'm going to take the log in the base a of both sides. Okay. Now I can use this property 3 over here, meaning I can bring down that exponent. So property 3 of the logarithms, that can come down. So I can rewrite this now as, my y times the log in the base a of b is equal to my log in the base a of x. Now I can simply divide both sides by that logarithm. Let's do it right here. Cancel that. So what do I get? I get y. This is equal to y now. Bring it right up here. Is equal to my log in the base a of x over my log in the base a of b. But what is y equal to? This. So I have this special property that changes from one base to another base, and I can simply write it in this simplified form. And that's what we call a change of base formula. Then what we do is we typically pick a couple of common bases, the common base as well as the natural logarithmic base to kind of do that. Let me just get this. The blue doesn't come off as easy as it used to. I've gotten a batch of slightly more adhering blue ink out of this mess. Most come out. Okay, so I have the following. So this now gives me my sixth rule for my logarithms, which is the change of base rule. And this tells me my log in the base b of x is equal to the log in the base a of x over the log in the base a of b. Now, this holds for any base a and any base b. So what we typically do is the following. We pick base a to be one of two types. So typically you'll see a form like this. Log in the base b of x is the base 10, or the common log, which we write as log of x over log of b. Or the second one, because these are both buttons on your calculator. The second one that you also see, and the one that I usually use more often than not, is the natural log. And here's our little proof of that change of base, if you will, formula now. Okay, so now we have all of these properties of logarithms. So what do we need to know how to do with them? We need to know how to do two different things. Well, we want to get practice working with them. So the two types of problems that we typically deal with are just like we did with the exponentials, either expanding them out into multiple logs or contracting them into a single logarithm. So that's what we're going to practice on doing today. And then you'll have some homework to look at that. And how do we use it? Well, we use it when we want to solve logarithmic equations. So there are two things that we want to, do with this. Two things to, learn. The first thing is how to take multiple logarithms and of the same base and contract them into single logarithms. So what you want to do is compact multiple logs into a single logarithm. And essentially just practicing these 6 rules. And then the other is just the opposite. Take a single logarithm and then expand into logarithms. And expand out. Okay, let's start with the first and see what we mean by that. Well, in fact, let's start with the second one. That's a little bit easier to do, and then we'll get practice, because the last one is what's more complicated. So I'll remember all these properties, but we'll use them from time to time, and then we'll also give you a few examples of Rule 6 over here. And how we use that. We used to use it when we just had calculators at our disposal, but now we have all these sorts of web applications that enable us to do it. And actually, in the calculators, you don't need to change the base on all calculators, because they are also built in to even the TI-84. So here's the first example that we're going to look at. And this is how do we expand logarithms using the rules of logs. So we might have something that looks like this, say the log in the base 2 of 16 times x to the 4th power. And how might I write that? Well, here I have a product over here. So I could write this product as a sum of the logs. So it could be log in the base 2 of 16 plus log in the base 2 of x to the 4th. Okay, then I notice here that, 16 can be written as a power of 2. Okay, so I could try that. If whatever you have here can be written as a power of that base, you should always do that. So that gives me 2 to the 4th power. and that's equal to 16. What can I do with this? Well, I have a property that says if I have an exponent attached to the variable in the argument, I can bring it down front. So that becomes a 4 times the log in the base 2 of x. Well, I can bring this 4 down if I wanted to. So I can bring that 4 down just the same way, of 2. But what is the log in the base 2 of 2? That's 1. That's our fifth property that we had earlier. So this is just 4 times 1 plus 4 times the log in the base 2 of x. So it's equal to 4 plus 4 times the log in the base 2 of x. Very simple. So I brought from a single logarithm to a expanded version where I just have log of a simple variable in the argument. Notice the only thing I have here is just the variable. Okay, so let me have you try this. You try a simple one. We'll expand this out. And see if you can expand that one out and see what you get. And I'll put the answer up here. And that's all it is. That sounds a little more complicated than that, but not sometimes not so bad. I'll try that one. Does anyone want to see how I got that? Everyone getting that? Okay, so let's just kind of plug it in and just see. This is a quotient over here. So what I can do is I can rewrite that as a log in the base 3 of x cubed minus log in the base 3 of 27. When I have a quotient, it becomes a subtraction. What can I do here? I can bring that down. 3 times log in the base 3 of x minus, I can write that as 3 cubed. That's what 27 is. What can I do? I can also bring that down. So I get 3 times log in the base 3 of x minus 3 times log in the base 3 of 3. But what is that equal to? That's just 1. So I get my final answer there. Okay, let's try another one and see if you can get this one. So we're expanding out. The harder one tends to be for some students just contract them in. So try this one as well. That's the natural log of square root of e to the x over e. Simplify that. Expand it out and simplify that. Now that gets rid of all the logarithms there. There are no logarithms there. And that can happen as well too. Does anyone want to see how I got that? Okay, so I have a quotient again. So I'm going to write that as the natural log of the square root of e to the x minus the natural log of e. Okay, that square root is a 1/2 power, so I can write that as natural log of e to the x all raised to the 1/2 power. The natural log of e, that's the same base, so that's just 1. That's that fifth rule of the x logarithms that I have. What happens for this? This can come down, so I get 1/2 the natural log of e to the x minus 1. Well, they're inverse functions of each other, so they cancel each other out to give me x, and there it is. So those are the sort of things you should be able to do using properties of logs, as well as some of the rules of exponents that will come up as well. Okay, so that's expanding out. Let's look at what some students find a little more complicated version of contracting and rewriting them in a different way. So let's take a look at the next group of problems. And now we want to do is take a series of logarithms and maybe some other things as well and contract them into a single logarithm. So here we want to look at contracting logarithms into a single logarithm. Let's take a look at examples. So say, for example, I have the natural log of 3 plus 3 times the natural log of x minus the natural log of 4 plus 4 times the natural log of x. Now we can combine some of these directly over here. So that could give me 7 if I wanted to. Like that. Okay, so what can we do? We got a lot of different logarithms. Well, one thing I could do, if I wanted to, I could leave it like this. I could combine those. I don't have to. If you do, I'm going to do it both ways. First way I'm going to do is without combining it. But I'm going to factor out a negative over here. So I can see I'm going to leave this the same for the moment. I'm going to change this very quickly. I can write this as the natural log of 4 minus 4 times the natural log of x. Now, it's not unique. You can do these in many different ways, as I'll show you momentarily. Then what I'm going to do is, and now I'm going to do the opposite. Usually I bring the exponent down. Now I'm going to bring the exponent up. Same thing over here. Usually I leave that exponent down. Now I'll bring it up. Okay. Here I can combine these. There's a sum, so I can combine those into, if you will, a product. So this is equivalent by essentially the first rule of logarithms, natural log of 3 times x cubed. That combines that way. Minus, this is a difference. So this combines into the natural log of I could write it as the natural log of, in this case, 4 over that. So 4 over x to the 4th. Okay. Now this is a difference over here. So how can that combine? Well, I can do that as a quotient again. So this can become, take this, it's a natural log of 3 over that. So it's 3x x cubed over 4 over x to the fourth. 4 over x to the fourth. Now I can take the reciprocal and move that up, and I get the natural log of 3x cubed x to the fourth over 4. And then I can add those exponents to get the natural log of 3x to the seventh over 4. So I could write it that way right there. Okay, that's simple problem now. Let's try another example over here as well. So try this one. I'll ask you to try this one. Try this one. So let's see if I take my 1/2 natural log of 5 plus 1/2 natural log of x minus 1/2 natural log of y. Okay, see if you can combine that into a single logarithm. I should mention here, I could have just combined those and that would have given me a seventh, and then I could have product and I would have the same thing. We'll put the final answer, what it looks like. I'll put it up above. I'll get the natural log of the square root of 5x over y. Anyone want to see how I did that? Okay. What I can do is, when I see a sum over here, I know that's a product, but that can't happen with a coefficient out front. So what I might do is I might factor out the 1/2. I mean, I could factor out the half from everything if I wanted to, and then bring it. Let's do that. Everyone has a half, so let's pull that out front. Like I said, there's many ways you can do this. I get the natural log of 5 plus the natural log of x minus the natural log of y. Okay, now I have a sum over here. That sum in the logarithm becomes a product. So it's 1/2 times the natural log of 5 times x. A sum becomes a product over here, minus the natural log of y. Well, this is a difference. The difference over here becomes a quotient of the two logs. So it's 1/2 times the natural log of 5x over y. So the difference here turns into a division here. That 1/2 is out front, so I can bring that up above. The natural log of 5x y to the 1/2 power. But 1/2 is nothing more than the square root operator, the square root exponent. That just becomes the natural log of the square root. That's what 1/2 power is, of 5x over y. That's all it is. Okay, let me give you another one to try over here. See if you can start to get the hang of this, but it takes practice. Definitely does take practice to do a lot of these things. Here's an interesting one over here. Let's try this one. I have 2 plus the natural common log in the base 2 of x minus 3 times the log in the base 2 of x plus 1. See if you can contract that into a single logarithm. This was a little bit more challenging because of this 2 over here. How do you handle that? That requires a little bit of foresight in terms of what you're trying to do. Remember, look at that constant 2. It's really of the same base. It's the same value as the base of that logarithm. They want to see how I got that contracted logarithm. First thing I see is subtraction here. So I know there's a division going on, but I can't do it with an exponent here. So the first thing I'm going to do is let me pull that up. I'm going to rewrite this as 2 plus the log in the base 2 of x minus the log in the base 2 of x plus 1 cubed. Okay, there I have that division. So that subtraction. Subtraction turns into division. So it's 2 plus the log in the base 2 of this divided by that. X over x plus 1 cubed. So that's what I did. I used the property that subtraction is division in terms of logarithm. But now there's a 2 out here. Well, this is what takes a little bit of interesting foresight. I could always put, remember this thing, log in the base 2 of 2 is equivalent to 1. That's one of our properties. Suppose I put the same base here and there and the same. So this is really 2 times 1. So I could replace this, which is 2 times 1, which is my log in the base 2 of 2. So that's equivalent to that expression. Plus log in the base 2 of x over x plus 1 cubed. Now in addition, I can bring that power up and write this as log in the base 2 of 2 squared plus log in the base 2 of x over x plus 1 cubed. Now this is an addition, so I can turn into a multiplication. Now I could square the 2. 2 squared is just 4. So I get it over here as my log in the base 2 of 4 plus log in the base 2 of x over x plus 1 quantity cubed. But here's a sum. Remember, a sum turns into a product. That means I multiply the 4 times that. So this is equivalent to the log in the base 2 of 4 times that x over x plus 1 cubed. And I can just put the 4 up top. Doesn't matter. And there I am. So now I've written in terms of a single logarithm. Now the purpose of this is we're going to see, this is what we're really driving at, because the next section talks about logarithmic equations. So meaning, let's go into the next thing. So 9.2 is properties of logs.